if xn, yn is in A, then P satisfies this inequality, and this then becomes less than 2 to the minus n h of xy minus epsilon. But now the terms in the sum don't depend on little x and little y, so we get a epsilon super n 2 to the minus n h of xy minus epsilon. Aha. 1 is greater than that, therefore this set is less than 2 to the n h plus epsilon. So that proves number 2. Now let's prove number 3, which is the crucial one. Number 3, we're interested now in the x tildes having the right marginals, but having the wrong, but being independent. 3. So let xn tilde, yn tilde be drawn according to P of xn tilde, P of yn tilde, where the P is the original marginal for the xy process. All right, then the probability that randomly drawn xn tilde, yn tilde are jointly typical is equal to summation over pairs that are in A, but now the mass associated with xn tilde, yn tilde, the probability mass, is the product, P of xn tilde, P of yn tilde. It's not P of xy, because they're independent, but we know it's the product of these. But this is for xn tilde, yn tilde in A, so therefore, this quantity is less than 2 to the minus n h of x minus epsilon. And this quantity is less than 2 to the minus n h of y minus epsilon. Aha. And the number of terms is 2 to the n h of xy. So I ran out of blackboard. Two to the n, the number of terms, plus epsilon, times 2 to the minus n h of x minus epsilon, 2 to the minus n h of y minus epsilon. Aha. But h of x plus h of y minus h of xy is the mutual information from very early in the course. And so this is equal to 2 to the minus n I of xy. And then here we have a plus epsilon, plus epsilon, plus epsilon. Since there's a minus in front, this is minus 3 epsilon. And that proves number 3. So the probability two independent things are seen to be causally related is 2 to the minus ni, where I is the mutual information of cause and effect. Let's take a 1 or 2 minute break, and when we come back we'll outline, well, we'll start to prove, and I hope I can prove, but I don't think I left enough time, the achievability of R less than C. All right, break, 2 minutes. Yeah. They look like, oh.
To me, this looks stronger.
Oh, yes, yeah, yeah. This is product P of xi tilde. Yeah, it is.
Now
This is product, yeah, P of yi tilde. Yeah, yeah. This all works for jointly ergodic, too, where you, for entropy, you substitute entropy rates. Yeah. So, in particular for,
To prove that, we just have to assume this.
what do we do with it?
So to prove this,
Yeah,
we just have to assume. So that we just
That's
use
right.
this anyways. This is like
yeah. On the other hand, no, unless this were IID, according to this, you don't get the 2 to the minus n I. You get I of x super n, y super n.
oh yeah.
Yeah. Right. Okay, here's the theorem. Channel coding. Oh, I know what I'll do. I'll go through it fast and then I'll review it briefly at the start of the next lecture. All right, there exists a sequence of 2 to the nr n codes with maximal probability of error going to 0 if the rate of the codes is less than the channel capacity. So, here's the proof. we fix P of X and R. And now we're going to generate a code. So we generate codebook. C, according to P of X. What is that? C consists of a lot of 2 to the NR code words, of block length n, and every element, this is x11, x12, x1n, down to x2 to the nr, 1, blah, 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 blah. These are all IID according to P of X. So, for example, for a binary symmetric channel, you might let P of X be 2/3. And then every code word here would be a sample from a Bernoulli 2/3 process. It'd have roughly 2/3 ones and 1/3 zeros. Similarly, 2, 2, 2, 2, 2, everything's independent. That's a code book. It turns out P of X equals 2/3 is not good. You're not using the full space available to you of code words. It's not the capacity achieving prior distribution on P of X. That would be a half in the case of the BSC. But in any case, that's what the code book would be for this P of X. All right. And I'll write it. It's just this way, really. This is sort of xn of 1, xn of I, and the final xn of 2 to the nr. So those are my code words. Now, I'm going to reveal C to sender and receiver. Sender needs it so he can, when he wants to send I, he sends the I's code word. Receiver needs it so he can do the decoding. That should be an alarm signal. Wait a minute. I have this channel. I'm going to use it n times. I'm going to send bits over it. And I want to know how many essentially noise-free bits I can get over in n transmissions. That's going to be NC. But wait a minute. If we follow this scheme and reveal C to sender and receiver, we have to send C to the receiver. This is a huge number of bits. Well, you can think of it as a setup, like that's the piece of hardware or a piece of software you give to the receiver. It's one time, and you're planning to use this channel many, many, many times. You can think, but there is a way for you to reveal C to the receiver that only takes about 6 or 7 bits, essentially none. Here's what you do. You say, I'm going to tell you what P of X and R is. You come up with the best code, the one that minimizes lambda super n. The best 2 to the n r, comma, n code. There. And then we'll use that. Right, so the receiver gets this, and it takes him like 2 centuries to find the best code, but you have specified it exactly, and it hasn't cost you any bits. So the fact that we reveal this code, the code book to both sender and receiver should